Good afternoon, everyone. Our lecture today is about Introduction to Machine Learning, and we're going to talk about some of the basic concepts of machine learning, which are going to lay a foundation for the tools that we are going to apply later. The topics of the discussion include curve fitting, classification, and the three very important terms: training, validation, testing, that are used in the machine learning literature. And we're going to conclude with some examples of supervised and unsupervised learning. So let us start with our favorite problem, which is the robot tracking problem. So what we are given is the sensor noise model and the robot motion model, and you know well that those are given or specified in the form of probabilities, conditional probabilities. And we were interested in estimating the position or the current state of the robot from the current sensor data. And we developed some tools last time, namely the particle filters and the Kalman filters. But that was the old problem. A new problem is slightly different. Here we start with an assumption that assuming our sensor is perfect, it is an ideal sensor. An ideal sensor has zero noise. So that is known, but what is not known is the robot motion model. So we need to figure out how the robot is going to move, but we are given the sensor information, the sensor data, and the sensor information is perfect. So what is a possible solution here? The one solution, which is very intuitive, is to just follow the sensor output. So essentially, if you look at the graph here, the robot position as perceived by the sensor, imagine if a robot is moving in a 2D plane, then here, just for the sake of simplicity, I'm plotting the position of a robot with respect to single axis. You can just call this as the x-axis position of the robot here. And on the horizontal axis, we have time. And so if we sample robot position at regular intervals, we are going to get some data points plotted on a graph like this. So let's say we have data up to time instance number 7. And our goal is to predict the position of the robot at the next time instance, that is time instant number 8. So that needs to be found. And so one of the things that comes to our mind is to apply curve fitting, so that if we can learn the pattern in the data, then we'll be in a very good shape to predict what is going to be the data point at the next time instant. So that's one instance where you can apply curve fitting to determine the position of a robot. And I imagine that students have sufficient knowledge about curve fitting based upon the subject of numerical analysis in the second year, perhaps. The simplest type of curve that you can fit to these data points is naturally a straight line. An example straight line is shown by a dotted line on the graph, and it is a classical regression problem, linear regression to be specific. So in linear regression, we are given a data set, data points, a set of data points, and each data point has two components, as in this case, x1 and x2. And our job is to calculate the coefficient of the straight line, that is a0 and a1. And you know very well that that can be found using least squares solution. So once we have fitted a straight line to the data, we can estimate the position of the robot at time instance 8. So we can expect robot to be somewhere over here. An important assumption behind regression is that the pointwise difference between the fitted line and the data points is distributed according to the Gaussian random variable. So again, you can see the vertical bars on the graph. They are showing the pointwise difference between the fitted line and the data points, and we say that regression will be valid only if these vertical error bars have Gaussian distribution, and therein lies the connection between the regression and the techniques that we have already discussed, such as filtration. In particular, the Kalman filters, where we assume that all the noises and uncertainties follow Gaussian distribution, and the same is the case here. Significance of this vertical error bar is that it represents error in the motion model calculated with respect to the ideal sensor data. Right? So in some sense, it is representing how closely the motion model agrees with the output of the sensor. All right, let's move on. Now, apart from straight line, we can think about fitting a generic polynomial to the data. So for instance, in this case, we are trying to fit a third order polynomial, and so we're going to find out the coefficients a0, a1, a2, and a3 based upon the x1, x2 data point values. And you can see here that the third order polynomial is a much better fit than the straight line, and the estimate will be somewhere over here. So we can expect our robot to be somewhere over here if we assume that the robot motion model follows a third order polynomial trajectory. Likewise, we can think about fitting a polynomial of even a higher degree. So in this case, we are trying to fit a sixth order polynomial, and we are trying to learn as many as 7 coefficients based upon the given data. And when you fit this polynomial, you find out that it is passing through all the data points, and the expected position of the robot at the next time instant will be somewhere over here. Now, although the sixth order polynomial seems to be a perfect fit, it is connecting all the data points, but the prediction is somewhat questionable, and it doesn't really appeal to our common sense, because what we really expect is that the x coordinate of the robot is manifesting an increasing trend. So it must be somewhere over here, and that's what the straight line and the third order fit told us. So this is something strange, that even though the fit is getting better with the increasing order of the polynomial, but we may not be getting a very correct prediction. So therefore, we can say that a sixth order polynomial is a perfect fit, but the predicted robot position is somewhat doubtful. So what we have seen here is an instance of overfitting, right? So if we try to put things in perspective and try to summarize what we have learned so far, is that if you try to fit a low degree polynomial, then it may not pass through all the data points, but at the same time, the low degree polynomial has fewer coefficients that we need to learn. So it's a simple task. It poses a reduced computational complexity. By contrast, the higher degree polynomial
such as in case of 6-degree polynomial that we have just seen, it may connect all the data points, but then that comes at the cost of learning large number of coefficients, because the number of unknown coefficients that we need to learn increase linearly with the degree of the polynomial. But an important consequence of fitting higher and higher degree polynomial is overfitting. That is, the polynomial, a high degree polynomial, may not be very good at predicting what we are trying to determine as far as the next position of the robot is concerned. And so one of the things that comes to our rescue is called Occam's razor, which tells us that the simplest explanation is the best explanation. In other words, a simpler curve is a better curve. In other words, Occam's razor is telling us that we should avoid all unnecessary complexities while learning about the data. Therefore, if we can come up with a model, a polynomial, which is simpler and it adequately connects the data points, then it is sufficient for our purpose. Now, moving forward, this curve fitting is a special case of machine learning. It is a way to discover the underlying patterns in the unknown data so that our system can learn to predict well the future data. And that is the main problem of machine learning. It actually comes in several different flavors. We talk about supervised learning, unsupervised learning, statistical learning, reinforcement learning. And all of them, they find tremendous application in various fields of science, engineering, and technology. So the two aspects of the machine learning is the characterization of future or unseen or unknown data by using or utilizing the knowledge of given or seen data, the data that we have seen. So it is a way to learn, it is a way to think about characterizing something that we have not seen or something that we may encounter in future based upon our past experience. Hence, as our experience grows, so does our ability to progressively improve the characterization, because with the accumulation of knowledge, we can predict well, we can make better guess, we can estimate the future outcomes of the future data in a much better way. An important concept in machine learning is the learning curve. And this learning curve says that if our guess about the future or the unseen data improves over time, it is an indication that we are learning. And I guess most people would agree with this definition. So if we try to plot the accuracy of guess, which is how well can we predict the unseen data or the future data against time, then we may see a curve which has an overall increasing trend up to some fluctuations. So this is how a typical learning curve for several machine learning algorithms look like. And you should also remember that the fluctuations are part of the learning process. So you should be brave enough. This time axis is usually proportional to the number of training data samples, right? So like we said before, that with the passage of time, as our experience grows, so does the data that we have seen and characterized, and therefore the number of training samples can also be plotted on the horizontal axis instead of time. So just a quick reiteration of what we have just said is that with the passage of time, the training data increases. That is the data that we can use to train our systems. That increases, and therefore that improves our ability to make better guess at the data future value. So here we are trying to formally define the concept of training. So remember, training is a process in which we are trying to compute the parameters of our model, which is trying to make sense of the observed data. And in case of the curve fitting problem, the training was about finding the values of the coefficients such as A0, A1, A2, and you can go all the way to A6 for the case of 6-degree polynomial. So calculating those values is part of your training process. Once you have trained your model or you train your system to think about the underlying patterns in the data, the next step will be the testing of the model. So in case of curve fitting, testing will be in the form of either interpolation or extrapolation. And I guess people are familiar with both these concepts. So how good is your system in case of curve fitting? Extrapolating or interpolating marks the accuracy of testing. So a good curve will be good at guessing the interpolated or extrapolated values that have not been seen before. So other than training and testing, there is another important concept known as validation in machine learning. So why do we need validation? Well, let's think about the case of overfitting and its an opposite, the underfitting. So we saw that a few slides ago that the 6th order polynomial is a wonderful fit. It passes through all the data points, but it was not very good at predicting the position of the robot at the next time instant. Likewise, if your polynomial is overly simplistic, such as 0th order polynomial, a straight line with zero slope, such as this, that may be just too naive, and it suffers from the same fate that the prediction accuracy is very small. So the 0th order polynomial is too simple, it's overly simplistic, and the 6th order polynomial is overly complex. And these two correspond to the case of underfitting and overfitting. And both these situations are bad as far as prediction is concerned. So how do we avoid overfitting and underfitting? Between testing and validation, we'll introduce a concept of validation. Validation is a process of choosing an appropriate model or hypothesis, in this case the polynomial, to avoid under and overfitting. And the way we are going to do that is that we are going to divide our data available for training into two sets. So whatever data that we can use to train our system is divided into two sets. One of them is the training set and the other one is the validation set. And usually the split goes 80-20, but it can differ slightly as well. And taking into account the portion of data for the purpose of testing, the overall recommended breakdown of your data would be that 65% of data will be used for training, 15% for validation, and 20% for testing. And the application of the validation process is that an unfit polynomial will manifest large error on validation data, no matter how well it is trained. So in some sense, if you think about a way to differentiate between a training and validation, is that in training we are trying to learn the parameters of the given model. So we select a model, a polynomial of a specific degree, and then we train it and we try to calculate the coefficients a0, a1, a2, and so on, depending upon the number of coefficients. But in case of validation, we are trying to evaluate different polynomials. So we are trying to see how well the polynomial of degree 1, such as straight line, is going to work as compared to, let's say, the polynomial of degree 6. So in validation, it is about the comparison of different models that we need to fit to the data. In case of curve fitting, in validation, we are trying to evaluate different curves and see which one would work better. But in training, we are trying to calculate the parameters of a given model or the given curve. So that is the main difference. Conventional machine learning paradigm, the process flow is that we're going to talk about training, followed by validation, followed by testing. So I'm going to set up an example, again the same one that we have just seen, and in this case, suppose the total number of data points that we have at our disposal is 10, and we have two candidate curves, cubic polynomial and the logarithmic polynomial. So if we go by the rule, the recommended rule, or the rule of thumb, I'm going to split the 10 data points into 6 for training, 2 for validation, and the remaining 2 for testing. More specifically, I'm going to use first 6 data points for training, the next 2 for validation, and the last 2 for testing. What this means is that the first 6 data points will be first revealed and no other data points will be available. So only these 6, the first 6 data points will be available for training. Then we have next 2 for the validation, and then the last 2 for testing. So now suppose that we fit the 2 curves. One of them is a cubic polynomial here, and the other one is a logarithmic curve. And when you fit both this curve by the training, it means that we learn the parameters of the 2 curves, and the parameters for the logarithmic curves were m and n, and in the case of the cubic polynomial, they were a0 through a3. And after the training process, you can see that the cubic polynomial is a remarkably good fit because it is passing through all the data points. That is not to say logarithmic fit is bad, but it looks like cubic polynomial is going to win just because it accurately fits data points. But hey, we need to wait here because it may be the case, as we saw before, that a very good fit may not be good at predicting. So it's a check for the overfitting, and we're going to do that by applying validation. So in validation, we are now going to compare which of the 2 curves performs well on the next 2 points. So these are the 2 new data points to be used for the validation, and you can see that the blue curve is fitting the 2 new points. So and these points were not available at the time of training. And so the cubic polynomial has essentially failed on validation. So despite the fact that the logarithmic fit did not connect all the data points, because it has a substantially higher performance or accuracy, I should say, we're going to proceed with the logarithmic fit, and the validation process has exposed the weakness of the cubic polynomial. I'm now going to release the last two data points for the purpose of testing, and these data points were not available until now. So the validation was performed using data points number 7 and 8, and the first 6 were used to train the two curves. And you can see that the logarithmic fit continues to perform well on the testing data as well. So that describes the whole process, and it is a typical process in machine learning applications and algorithms. Homework exercise, I would encourage students to utilize and explore the MATLAB curve fitting toolbox, and you're going to try various subsets for training, validation, and the testing data, and see how this process that we have just learned works. So far we assumed a temporal relationship between the data points, and we said that the first 6 were used for testing, the next 2 for validation, the last 2 for testing. But you can also think about taking the first point and maybe the 6th point for testing perhaps, and this one for validation, and the rest for the training, and see how this process goes. Machine learning is about categorizing the data points, and we specify a category by means of a label. And in a very simple case, you can think about a binary labels where a data point may be assigned a label such as a good, bad, low, high, benign, hazardous, true, false, etc. So let's look at a simple example of a DC motor loading regions. And here the available data, perhaps we obtained this data by performing experiments on a given DC motor. And this data points represents the torque and the speed, and perhaps we need to reorder the two parameters, so speed should come on the left and torque on the right. So I'll try to fix that one. So anyway, so this torque speed data points are available, and one might be interested in asking what might be an appropriate label for this data point. So remember, the value of speed and the torque of the data point represents the value. It's not the label. Label really refers to something we can say about characterizing the data, or a qualitative assessment of the data. So what are some of the labels that we can assign to the speed, torque data points? So in case of DC motor loading regions, you can say that if a given load can be driven by the motor or not. So a given value of load torque and load speed either represents a feasible load, or if in feasible load means that the motor can drive this load, you can run your motor which is capable of running this load at the given torque and the given speed. But it may be the case that the load is infeasible, meaning that the motor cannot run this load at a given torque and speed. So we have come up with some labels here: feasible, not feasible. And so we are now asking which of these data points represent feasible load and which represent not feasible or infeasible loads. So what is a recipe to discriminate between feasible and the infeasible load? And I think the answer is simple. Recall the torque speed curve, this blue curve here. And so this torque speed curve is obtained by running the DC motor at the constant power, and that defines the boundary between the data points. So some of the data points will be falling below this curve and the others will be lying above this curve. So at this point, can you think of the labels for these data points? So what can you say about the labels of the data points which are lying above this curve? And what about the points which are lying below this curve? So quite naturally, any point which lies below the motor torque speed curve represents feasible load. That's because the value of the torque and the speed of any data point which is below the curve has torque which is less than the torque that motor can provide, and the speed, the corresponding speed, is less than the speed at which the motor can run, right? So this vertical difference again. And similarly, if you look at the encircled data points, they represent infeasible load because they represent values of either torque or speed or both, which the given DC motor cannot achieve. So this boundary is very insightful. It is splitting our data set into feasible and infeasible load data points. So this example leads us to the paradigm of supervised machine learning, the most widely studied form of machine learning, where you're given the data points, means the values, but you're also given the labels. The labels are also given, and you need to find the separator. So for instance, in case of torque speed example that we saw earlier, you're given two different types of data points. The one represent the one type of data point which are represented by the cross, the other one by circles, and your job will be to find out that boundary. Where does this boundary lie that separates the circles from the crosses? That boundary is known as a classifier. The most simple, maybe I should say, what people believe is a simplest classifier in machine learning is a straight line classifier, and they're often known as perceptron. And we're going to talk about perceptron learning, how you're going to train a perceptron in our next lecture. But then in many real life applications, this may not be adequate, and the boundary may not always be represented by a straight line. In practice, you often need a nonlinear classifier, which is naturally more complex. It is more complex to train because of large number of parameters. Just as if we try to train our system using sixth order polynomial, you're learning large number of coefficients, as many as 7 coefficients. But then it has several practical applications. And one of the main example in case of nonlinear classifier is that of the artificial neural networks, which remains an integral component of our discussion post midterm. In contrast, we have another paradigm of machine learning known as the unsupervised machine learning. So this word unsupervised to me is somewhat scary, and the main reason is that although the data points they are given, that is the values are given, x1 and x2, although in this case I've used x and y, but the scary thing is that the labels are not given. The data labels, they are missing. And then the problem asks you to categorize the data points by making clusters. And there are several practical real-life examples which map to the problem of unsupervised machine learning. So I'm going to quickly describe a problem that you may have covered in the robotics course last semester. It is about constructing a roadmap that provides maximum separation from the obstacles on the either side of the robot. And this roadmap means an obstacle-free path. So in a sense, we have to find an obstacle-free path between the obstacles as your robot tries to navigate through this arena. So here, this figure represents arena, the x-axis and the y-axis here, and these circles indicate the sensor data has sensed an obstacle. So all of these circles, they represent the presence of an obstacle. But the main question, and obviously they all look pretty much the same, assuming that the obstacle, so either you can assume that the obstacles have a similar structure, or you can just say that sensor output gives you 1 and 0, so that all these data points, they are representing a value indicating an obstacle. They don't have specific labels on them, right? So to solve this problem, we construct a Vernier diagram. And those who are not familiar how to construct a Vernier diagram, it is a partitioning algorithm where you partition your given data points into given number of classes or partition such that all the data points within any partition, they are closer to the centroid of the partition. So they are closer to the centroid of that particular partition than to the centroid of any other partition. So all the data points in this partition are closer to the centroid over here. And you can see animations, you can refer to the internet resources, you can look at the literature how to construct this Vernier diagram manually. But let's say this is what the algorithm comes up with. So we have 4 partitions, and these boundaries represent the roadmap. So your robot can navigate through the arena by following this obstacle-free path. An important consequence here is that the algorithm has learned that there are 4 obstacles by making 4 clusters of the data point, by dividing data points into 4 clusters. But naturally, the number of obstacles can be different. It can be more than 4, it can be less than 4. So here the algorithm is going to cluster all the data points representing the presence of obstacles into 6 clusters. And the resulting roadmap looks slightly different. So this roadmap tells us that the robot can navigate through this arena in a way that it has a bit more freedom. So you see that this particular path was missing last time, and so was this. And that begs an important question, that who gets to decide in how many clusters are we going to group our data, or in how many obstacles do we need to assume? And a natural answer to this question might be the prior knowledge of the arena and some other information about our system, such as robot. How big is our robot? Because if the size of the robot is large enough, then it may be very difficult to make it go or pass through a path where the obstacles are very close by. And so this always remains an open question in unsupervised machine learning. So I encourage all the students to think about different opinions and approaches about the selection of the numbers of clusters that one should be used to group data when the labels are not given. Now, before the midterm, we extensively covered the problem of simultaneous localization and mapping, the SLAM. Your homework exercise is to figure out what kind of learning process does the SLAM represent. Is it supervised or unsupervised? So I'm going to conclude my lecture today and the lecture for this week with the topic of our next lecture, that is the perceptron learning. So those who are interested can get a head start, and I can share some slides with you on the Microsoft Teams. So that's it. Thank you very much, and I hope you have a nice weekend. And we are going to see you tomorrow for the question and answer sessions, or perhaps I guess it should be scheduled on Thursday instead. So I will let CRs know the time and the date of our Q&A section. Thank you very much and have a nice day.